Unit 8. Really nothing new. It's just kind of a combination of a couple things we've done before. Match the pairs design and doing confidence intervals and hypothesis tests for one sample means. Okay, so that means a t-interval and a t-test. Anybody familiar with this author? Michael Crichton? No? He wrote another famous book that's been made into several movies, and I think there's another one coming back again, Jurassic Park. So, anyway, he wrote this book called State of Fear, and part of it was on climate change. And so this book, like it says here, it depicts eco-terrorists plotting mass murder for the sake of propping up their false theory of global warming. And it's framed as fiction, but it has tons of graphs of real data, footnotes, scientific articles, and a huge bibliography. And it was a bestseller, and many climate change skeptics who don't believe in climate change point to this book. And one of the reasons was in the book, they talk about a certain weather station, Punta Arenas, which is located basically on the tip of South America, so very close to Antarctica, which actually, if you look at the graph here, this is the temperature in, what was it, it's hard to read that, it's the 1950s or something like that, and it actually declined over time. It didn't go up, which many people often say, which is happening with the happening in the world. Can you see something wrong with that right away? As a statistician, why would you be skeptical of this?
One place.
It's just one place. Exactly. Okay. So what does the general trend show here? Well, it shows a gradual cooling. Goes against a lot of science. Says Earth is warming. So some more data. The average temperature from 1901 to 1950, 6.828 degrees Celsius. From 1951 to 2000, it went down slightly to 6.52. So if I take the difference between the later temperature average and the earlier year temperature average, I get negative 0.076 degrees Celsius. Okay. So the negative means that it actually cooled. So it tended to cool down. So as you said, Brooke, I mean, the first thing you look at, you say, well, that's one That's one station. There's got to be several stations around the world that we can study and come up with probably a better conclusion, more statistically sound. I'm sure enough there are. Okay, and there's over 7,500 stations in the world. So what was done was a sample of 32 of these stations, a random sample, was selected out of the 7,520. And then the data was analyzed. So for all of these places, all 31 of these places all around the globe, right? From 1901 to 1950 temperature, from 1951 to 2000 temperature. And if it's positive, that means it warmed. Because remember, we're doing this, subtract this. If it's negative, it cooled. And so what we did here is a matched pairs structure or matched pairs design. Why? Because instead of like taking one group, say a control group and then a treatment group, okay, we took each of these stations that we randomly selected and we compared temperatures within itself, which is the very definition of a matched pairs. So it is matched pairs because each individual station has two measurements. So we are finding differences within each individual or station. Within each station. And what's so good about matched pairs? It controls for variation as opposed to just taking, say, 16 of these stations, putting them into one group, and 15 putting them into the other group, because you'd have a lot of variation within the group. So that's the big advantage of matched pairs. Okay, so matched pairs controls for variation in weather patterns. So like I said, if you took a group of 16 and then found their average difference, and then a group of 15 and found their average distance, there's a lot of variation. So the results may not be as strong as if you did a matched pairs design. And you can see here, just by looking at the differences, there's not many negatives. So there's not many stations that experience cooling from the first half of the 20th century to the second half. And we can see that if we put these 31 station differences on a dot plot. Okay? So negative means cooling took place. Positive means warming took place. And it seems to be pretty obvious what's happening here. Only what, if this is slightly below zero, 3 to 5 stations had cooling. Okay? Which means like 28 up to 28 at no change for warming. Okay. We can see here's where Punta Arenas is right there. Okay. Okay. So did more stations see warming during the 1900s or cooling? Well, how do we know? By looking at the dot plot. A significant of stations have a positive difference in temperature. Which is the same as 1. This next one is sort of another common sense one. Does Punta Arenas appear to be representative of the general trend? No, absolutely not. So no. Which means we are skeptical. Evidence against global warming. So how can we go further and use statistical methods? Well, first of all, we're going to find the sample mean of all the stations. So we're going to average up all the differences, but we're going to average all the differences. And it turns out that is 0.35 degrees Celsius for warming. So if I put that on the dot plot on the previous page, so 0.35 would be there, which seems to make more sense because even though the data is spread out, it's still kind of centered around this. Like these are kind of, there's a group and almost an equivalent number that are below and above the sample mean. So, I mean, we could say that this is roughly equivalent if we were asked to describe this dot plot. So is the sample mean, just as I said, yes. Because the data while spread out centers around a difference of 0.35 degrees. Centers around 0.35 degrees Celsius. Yes. Okay, so how do we do this statistically? Well, remember, we're dealing with means here, okay? And we're dealing with, even though it's two measurements from each station, we're only using one measurement, the difference. So that is equivalent to one sample. So therefore, we can do, okay, either a one sample confidence interval for means or a one sample hypothesis test. And we've already done those in this unit. So what we're going to do is go further and come up with a better conclusion, one that's more statistically significant, by doing the four-step method. We'll do a confidence interval and a hypothesis test. So we know that the difference is 0.35. You need to be told this. Oh, sorry, there were 32 stations. But you do need to be told the standard deviation of the differences. Okay, so you are given that. So how do we do this? Well, state, what are we doing? Constructing a confidence interval, or a CI, and then we'll just call it this. Remember, this is for the population, so we use mu. This is not the sample. We're using the sample to help us answer about the population, which is true global average difference in temperature. Plus to the planet. This is where you state one sample or two sample, and T interval or T test, or Z interval or Z test. Remember, if it's means, T. If it's proportions, Z. And it's one sample, the differences. So one sample, T interval. For the true global average difference. Yeah. Random. 10%. And normal or large sample. Remember, large counts is with proportions. Large sample is with means. Well, stations were randomly selected. "32 stations is definitely less than 10% of the 7,520 stations that we chose from. And 32, the sample size is also greater than 30, which allows us to assume normality. So do stage, you got to get the right function on your calculator. It's going to be a T interval. So down to the tests, to number 8. Always choose stats, and then it's just telling you what to enter. Okay, so once you get, if you got the right function on your calculator, it's going to tell you everything you need to enter, which you're going to be able to get from the question. So the sample mean is 0.35. The sample standard deviation is 0.296. N is 32. And sea level, we have 95, I think, right? Yeah, 95. You have to enter it in decimal. And that will get you your confidence interval. Remember, this is the difference. So if it's all positive, that means warming took place. If it's all negative, that means cooling took place. If it's a mix of both, we can't actually be sure. Yeah.
And any of these like long answer questions, like 17, will they ever kind of have you like solve for like one variable in there that we're missing now through all the year?
You're going to be asked. You're going to be asked to construct a confidence interval or perform a hypothesis test in which you calculate the p-value, or which this calculates the p-value. No, because then you would have to use those other formulas the long way. Okay, so we've got 0.35, we've got 0.296, we've got 32.95, and should be no surprise that they're all positive. All the differences in the interval are positive. Because we could see that from the dot plot. Okay? So the conclusion, remember how we conclude a confidence interval, we are 95% confident. Interval .24328 to 0.45672 captures the true mean difference in temperatures. Okay. Now we could do the same thing. So that was a matched pairs T interval. We could also do a test. And do you think, remember the test, we always compare the probability value we get against the alpha value. Do you think that it's going to be lower, which means we reject the fact that there's no difference? Just by looking at this. Remember, the null will be no difference. The alternative will be, yeah, there's a difference. It's a positive. Yeah, we're gonna reject HO. Because if we look at the confidence interval, okay, they're all positive differences. So you can see how the two relate to each other. So same kind of thing, except now we're just going to do a test. We won't review the conditions. We'll just assume that they were met from the previous. So state, and this is where you state your null and your alternative. Where mu d is the true mean difference. Temperatures. So our no difference, which means the true difference will be nothing, will be zero. But if there is a difference, and if it's positive, which means that's what we're trying to establish. So we're trying to establish that there's warming. We're not trying to establish that there's cooling. So that's why we say greater than zero. Remember, greater than zero means there's warming. Then the plan. This would be a one sample t-test. Difference if, and then remember we already did this in the previous one, so we'll just write conditions now. Don't rewrite them again. So on the graphing calculator, we're doing t-test. So when you go to t-test, and again, stacked always, you're asked for the no mean, which is 0 equals 0. You're asked for the sample mean of differences. You're asked for the standard deviation of the sample mean. You are asked for the sample size. And then you are asked, are you trying to prove not equal to, greater than, or less than? We're trying to prove greater than 0. And when we do that, we're going to get a bunch of values, but we only want to focus on the p-value, which is approximately 0.701. Really small. Looking at me funny. Zero. 0.35, 0.296, 32. Yeah. 8.78 times 10 to the negative 8. So conclude, because our p-value is less than our alpha value, 0.05, I think it's 6 seconds. Yeah, that's so an alpha value. We reject HO. We have convincing evidence there is a positive difference, which means warming, And this last question I alluded to a little bit earlier, how is confidence interval consistent? Well, that's 0 is not in our confidence interval. Therefore, we can go with this sentence. We have convincing evidence there is a positive difference in temperature. Okay. So like I said, nothing new there. The big thing is recognizing a matched pairs. So